What's going on, physics students? We're going to be covering some two-dimensional motion stuff. I'm going to go through this kind of quickly because today is actually a really important day. I want to run a lab with you guys, and I basically want to cover vectors and physics with you. So please, 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 if you can, besides Julia, make sure you guys come in this coming Friday. Also, come in next Friday as well because we're going to have that Grit Fest thing. It'd be awesome if I had you guys inside my team. All right. What I'm going to be covering...
Time?
What is that?
What time?
Grit or time for lab on Friday, this Friday. Come in from 10:30 to 12. All right, and then the Grit Fest, I think it's an all-day thing. But anyway, let's get started with physics today. We've been covering two-dimensional motion, and two-dimensional motion wasn't that bad. When I shoot a cannon horizontally like this, and the cannonball is gonna fire and basically fall to the ground like that. It's gonna follow this parabolic arc, right? And we've solved this. In fact, I will. Yes, of course, Julia, the WebEx will be recorded. In fact, I might not broadcast it online because I want to make sure that. Anyway, we'll talk about that. But let me tell you how we solve this. I shot something out horizontally and went beep, 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 hit the ground, right? And then in order to solve this, let me kind of just take you guys through the grand scheme of things, the idea of what's going on. Basically, we want to figure out how far this thing goes. So we want to calculate what R is. What we did was we figured out, we said, all right, well, I don't know how to do physics in 2 dimensions, but I do know how to do physics in 1 dimension. And I even showed you guys a video the other day where if you shoot a ball out this way and you drop it, then the only thing pulling down in the vertical direction is gravity. Meaning that if you drop a ball from the same height and if you shoot a ball horizontally from the same height, then what will happen is this balls will hit the ground at the same exact time. Then what we said is, I know how to figure out the time that it takes if I drop the ball from height h. I would be able to calculate t. And I believe, to be honest with you, I don't have everything memorized, but I believe the time was the square root of 2h over g. I would never memorize that, and I'm kind of even skeptical as to my answer there. I'm pretty sure that is the answer, but where I got that from was I basically applied it to the equation delta y equals v naught t plus 1/2 at squared. I'm sorry you can't see that. Let me write it again. Right here. Delta y equals v naught t plus 1/2 at squared. Do you guys see how I did that? I figured out time. Yeah, it's delta. So delta y is just h. Fine, I will solve it for you. Fine. Delta y is h. The velocity in the y direction is 0. And then this is 1/2 gt squared. So I just solved for t. So you multiply by 2, you divide by g, and you take the square root. That's the answer. So from dropping a ball, I was able to get the time that that ball was in flight. I was able to get the time that both of these balls were in flight. This ball was in flight, this ball was in flight. Does that make sense? And then knowing the time that this ball is in flight, I can take a look at the x direction and I can say, okay, since the x direction is moving at a constant velocity that way, and it's not speeding up or slowing down, I can simply multiply my velocity times my time to figure out what r is. So r is equal to velocity naught in the x direction times the square root of 2h over g. Are we cool? This is a review, by the way. Are we good? Yes? No? Help me out here. There's 5 of you guys here. You guys are great students. So, all right, awesome, awesome. All right. So that's how I was able to solve this two-dimensional motion problem. Now, I'm going to share with you guys another solution. Don't memorize this solution. We came up with that using the basic equation. It's delta x equals v naught t plus 1 half at squared. Don't ever memorize these solutions. Memorize what it takes to come up with them. Because this solution only works for the exact scenario that you are firing a bullet or a ball or something horizontally. Well, what happens if I fire it up at an angle? Or what happens if I fire it down? Or what happens if I'm standing on the ground and I fire it at an angle? By the way, take a picture of this, write this answer down because I'm going to ask you this later on. I'm going to come back to this. So write this down. I'm going to erase. Get ready? Take a picture. 3, 2, 1. All right, I'm assuming you're good. Okay, the next problem I'm going to solve is this problem right here. Here's the concept. Okay. This time, instead of firing it from a certain height, I'm going to fire it from the ground. And then what I'm going to do is I'm going to fire it up at an angle theta with a velocity initial of v naught. And I'm going to see how long it goes. That's what I want to solve for. I want to solve for r. I call r the range. That's what r stands for. So it stands for the range. It's the distance. It's your delta x. It's the same thing. The range is the same as delta x. I know that might be sloppy. Let me just rewrite that a little bit more. Delta x. So I'm looking for my delta x. Are we cool? You guys understand this? Now, the complication that we add in two-dimensional motion is this idea that we can use trigonometry somehow. And I don't think that I've even used trigonometry in these problems yet. Let me start, okay? I would argue with you that I don't know how to solve physics in two dimensions at the same time. I know how to solve physics in one dimension one way, and then apply that same information to the other dimension in the second way. Am I making sense to you? Does that make sense? It's just like the problem I did before. I broke it up into its vertical component first, and then I also broke it up into its horizontal component. So exactly, so I'm putting these two concepts together. So what I'm going to do before I start the problem is I'm going to just kind of break this up. I have a velocity initial at an angle theta, okay? What I want to do is I want to break this into two lines. Instead of having one line that's at an angle, I want to break it up into two arrows that is at horizontal and vertical. And I'm going to call this one v naught x, and I'm going to call this one v naught y. This stands for velocity initial in the x direction, velocity initial in the y direction. Are we cool? So, then what I'm going to do is I'm going to use trigonometry to figure out what v naught x is. V naught x is equal to what? Now I'm looking for the, now tell me, if this is the angle right here, which side is this? Is this the opposite side or the adjacent side? Is this the opposite side or the adjacent side? You have two answers. Guess. X is the adjacent side. What about you, Alec? What do you say? Or Justin or Catherine, what do you say? I'm going to wait for you. Alec is saying what? The adjacent side? Awesome. Okay, good. Adjacent side. Yes, exactly. The angle is here, so the adjacent side is the one that's right next to it. So it's this. So I'm dealing with the adjacent side. I have the hypotenuse and I have an angle. Which trig function am I going to use? I'll give you a hint. Which of these trig functions do I use if I have the adjacent side, or I'm looking for the adjacent side, I have the hypotenuse and I have the angle. And Justin says, that's not a hint. Okay, what is it then? Exactly, it's the cosine. It's not a hint. I told you the answer. I would use the cosine of the angle because it deals with adjacent and the hypotenuse. Fine. The cosine of theta, so I'm just going to do some side work for you real quick. The cosine of theta is equal to the adjacent side, which is v naught x over v naught. And if I want to solve for v naught x, I would simply go v naught x equals v naught cosine theta. I'm going to ask you, if you understand this, I'm going to ask you to write this down because I'm going to erase this right here. Do you understand this? Yes, yes. Okay, good. Then I'm going to erase, if that's all right. Can I erase it? Tell me yes. I'm just going to erase this part. All right. So v naught x is equal to v naught cosine theta. Can anyone take a guess as to what? There we go. Julia says this is equal to v naught sine theta. All right. If you don't believe me, prove that to yourself. Figure out how v naught y is equal to v naught sine theta. Actually, this is a really important concept. So do you need me to prove that to you? Do you need me to show you how v naught y is equal to v naught sine theta? Do you want me to show you that? If you do, say yes. All right? You love truth. That's awesome because we're going to really get it here. Actually, this is the only time we're going to use this concept and we're going to use it over and over again. The trig we're going to use in physics doesn't really get much harder than that. As long as you understand how to break this up into its components. I'm probably going to do it over and over and over again so you guys just start spinning this stuff up. All right. So here's how I'm going to solve the problem now. I'm going to say this. I don't know how long it takes or I don't know how far it goes, but it would be very helpful if I knew how long this ball was in the air for. So I'm going to isolate my view to only looking at the vertical component. Does that make sense to you? It's kind of like I put it's kind of like I put these blinders on like this. And I look at the ball, and I basically see it go up and down. You can imagine throwing a football away from you, and you would see it go up and down. You would only be looking at the vertical component of this. Does that make sense? Justin, by the way, I think you're personal chatting with me. Just put it in the regular one. All right, so we're going to isolate, what we're going to do is we're going to isolate the y-axis. We're going to look in the y direction. Oh, you can't see that. I'm sorry. That's too high. We're going to look in the y direction first. I'm looking to the y direction first. No, speaking in terms of math, this isn't the range. This is actually talking about just the vertical component. It's the vertical axis that we're talking about. So, in the vertical component, we have our five variables. We have a velocity initial in the y component. We have a velocity final in the y component. We have an acceleration in the y component. We have a time, and we have a delta y. Okay? Let me ask you this. What is its velocity initial in the y direction? I'll give you a hint. V naught sine theta, exactly. What is its acceleration in the y direction? In the y direction, what is this thing accelerating at? Delta y. No. No. There is an acceleration that is acting on this ball, and I'll tell you what. Here's a demonstration as to what I'm talking about here. All it is was we're figuring out how far this thing goes. That's all I'm doing. That's literally the problem I'm solving here. Exactly, Julie. It's gravity, because gravity is what is pulling down on this thing at all times in the vertical direction. So, by the way, I forgot to do something, and this is actually probably one of the most important steps, is I need to define a coordinate system. So I'm going to call a standard coordinate system. Positive x goes this way, positive y goes up. So therefore, my acceleration in the y direction is actually equal to negative g, which stands for negative gravity. Does that make sense? All right. The next. What is the time? Was I given that? Was that information I was given? Do I know that? I knew what the velocity initial was. I knew what the acceleration is. Do I know the time? No. But I did tell you that that was important information, so technically that is what I'm looking for. So I'll put a question mark by it. So this is important, this is important, this is important. What about my delta y? Did I tell you what my delta y is? This one's tough to think about. Think about what is your change in height over the whole motion. If you're confused, take something and throw it from one hand to the other. What is the change in height from here? Whoa. From here to here. What's the change in height? You got to think about it. It's tough. There is no change in height because there is no displacement in the y direction. Exactly. Very good. Your delta y is 0. Now, I told you guys that there's a special way to figure out which equation to use. By the way, if we have velocity initial in the y direction, we have acceleration in the y direction, we're looking for the time, we have the delta y, that leaves my v final as my dk dc. I don't know it, I don't care about it. Meaning, the equation I'm going to use is delta x equals v naught t plus 1/2 at squared. Of those 4 kinematic equations I gave you a couple weeks ago, that's the one I want to choose. But in this case, I would write a delta y equals v naught t plus 1/2 at squared. Right? And exactly. I can't tell if that's Julia or Justin because they both start off with J and that's all I see. But yes, it starts on the ground, it ends on the ground. That's why delta y was 0.
Yay. Sorry, my thing.
It's alright. It's alright. You were trying to talk to me, but the problem is feedback. Alright, so this is the equation I'm going to use. I'm going to plug in 0 here. So I have 0 equals v naught sine theta times t minus 1/2 gt squared. And I want to solve for t. Okay? I'm going to do this real quickly, not because I don't have time, but because I'm going to run out of space, I guarantee you. All I did was I took this 1/2 gt squared and put it onto the other side. I just added 1/2 gt squared to both sides. Then I'm going to divide by t everything. That will cancel out with this, and that will cancel out with one of those. I'm going to kick this 2 up there, and I'm going to divide the g downstairs. So I have t is equal to v naught sine theta times 2 divided by g. We cool? I have not shown you this before. It might be familiar. Well, maybe. Actually, you know what? I have shown you something like this before. Kind of. But are we cool with this? Can I move on? Okay. Now notice that this might freak you out because I didn't plug in any numbers. I didn't give any numbers. I didn't start off with any numbers. I just said you start off with some velocity, you shoot it at an angle theta. It's under the influence of gravity, which is only pointing in the vertical direction. I could plug in numbers if I wanted to. I could plug in 10 feet per second seconds as how fast I threw it at an angle of 20 degrees or something like that. But I'm going to leave things general for now. In fact, if you notice, I'll solve everything as much as I can in the general way, and there are great advantages to that. Let me show you some of them. Now what I'm going to do is, I know the time. If I plugged in the numbers, if I plug in 10 here, and I plug in 9.8 here, and I plug in 20 degrees there, I could calculate it out. I could shove it in my calculator and figure it out. Boom, that's your answer. That will be the time. Say it comes up with like 3 seconds or something like that. Then what I'm going to do is I'm going to take that time, whatever this gives me, and plug it in to the, now I'm going to look in the x direction. Okay? Let's list out our 5 variables. We have v naught x, we have v final x, we have acceleration x, we have time, and we have delta x. By the way, notice that the time here is the same as the time here. And that's kind of an important concept, but it's very easy to understand. There's no such thing. There is such thing as the x component of velocity, and there is such thing as the x component of acceleration. But is there such thing as x component of time? No, time is the same here and here, which is why I can take it from here and substitute it into here, by the way, just to let you know. What is v naught x? What is v naught x? By the way, I'm not doing this because I got a kink in my neck. I've got to just give me a hint. V naught cosine theta, exactly. So we have this. V final x, we don't have. We don't care. What about ax? Do we know what ax is equal to, by the way? I'm just curious. I wonder if you guys know. All right, okay, fine. Someone says it's the acceleration along the x direction. What is the acceleration along the x direction? We're not talking about, the path that we're describing is not the force that we're pushing it before. We're talking about when it's in free flight, after it's left the cannon or your arm or whatever. What is its acceleration in the x direction? No. No, what is its acceleration? No, acceleration is not a distance. Don't tell me about distance. What is its acceleration? Is it gravity? Think about that. What you're telling me is gravity is pulling me to the right? Is that really true? Gravity has nothing to do with it. Yeah, all right, I agree with that. What is the value of the acceleration? All right, you guys are throwing out a bunch of smart words. Okay, all right, I think that's Justin. I think I totally agree with you. Gravity only pulls in one direction. So therefore, in the x direction, what is its acceleration? I'll give you a hint. It rhymes with hero, starts with a Z, It's 0 because in the x direction it's not speeding up, it's not slowing down. That is, of course, if we're taking into account that there is no air resistance, because in the real world there would be air resistance, but very little in comparison to what, you know what I mean? Like if I threw this ball, the air resistance wouldn't really play that big of a role into the thing because the flight time is so small. But yes, exactly. When we're talking about only the x direction, we're talking about a 0 acceleration. So we have that information. We know that that value is 0. What is the time? I'll tell you what the time is. It's right here. What is its delta x? Well, goody, because the delta x is exactly what we're looking for. Which equation do we use? We use the exact same one. It's delta x equals v naught t plus 1/2 at squared, but I don't even need to write the second half of that equation because there is no acceleration. By the way, this delta x is also known as r, which is what we're solving for. So r is equal to v naught in the x direction, which is v naught cosine theta, times the time, which is 2 v naught sine theta, all divided by g, which is known as gravity. Okay? This is my answer. If it's alright with you, I'm going to write it a little bit prettier. Can I erase this a little bit? I'm just going to take the 2 and put it over here. I'm going to make it a v naught squared because I have v naught times v naught. That's all I'm going to do. Actually, you know what? I'm going to do it like this. I'm going to go v naught squared 2 cosine theta sine theta all over g. And I'll be honest with you, I don't remember off the top of my head, but can you guys go and open up a new tab, and I want you guys to go search for something. I'll wait, all right? This might take a little bit of time. Can you guys go look up trig identities? And Julia, I'm going to count on you to find this one quickly because you said you love trig. Look at trig identities. I want you to find something that looks like this. I don't remember it off the top of my head, but find out what sine of 2 theta is. I'm pretty sure that that's correct. What is the sine of 2 theta? I think that it's equal to 2 sine theta cosine theta. Can you confirm for me if that's correct? Go look it up. I'll pull up in a new tab, type in trig identities. It's been a while since I proved the range equation here. Make sure that this is correct. Find a website that tells you what the sine of 2 theta is. I think it's called the double angle formula. I could be wrong. Alright, I'm going to erase this. And I'm actually going to say I'm not wrong. I think that that's correct. There's a trig identity. I was wrong about the first proof. What first proof? What are you talking about? Anyway, Justin, you explained to me what I was wrong about, and I'll tell you whether I was wrong or not. And then why don't we talk about this one? There is a trig identity that says that 2 sine of theta cosine theta is equal to sine of 2 theta. So I want you to write this down as your range equation. Sine of theta cosine theta plus cosine theta sine of theta is equal to sine of 2 theta. That's what Julia says. Oh, okay. So if theta is the same, then that's saying 2 times sine of theta cosine theta is equal to sine of 2 theta. Yeah, all right, cool. I was right. Awesome. This is what I want you to write down. Now let's think about this, because this is where it actually becomes cool. This is where I'm going to get all excited about it, and you guys are going to be like, wow, my mind is blown. Make sure you write this down, all right? Okay. One of the things I know that you hate, because I hated this too. I've been teaching physics for almost 15 years now, and in all that time, I've never really met a student who likes doing it this way right off the bat. I used to hate solving everything in variables. But for the most part, I've been able to convince most students that this is actually much better. Even though it's harder, it's better. And I mean, that's kind of what I'm trying to teach you. I'm trying to teach you perseverance. I'm trying to teach you grittiness in mathematics. Like, you're going to get there inch by inch. And you're going to struggle, but you're going to get there. You're going to win. Even if you fail time and time again, you are going to constantly keep coming back to it. What I'm going to do now is talk about solving it in this variable form, because there's this great advantage of it. And I'll show it to you. You guys ready? How do I know that this is the right equation? What I'm trying to describe for you is, if I have a cannon, and I do have a cannon, I have a mini cannon right there, and if I shoot it, how do I calculate out the velocity, or the distance that it will go? Well, I can do it in a couple of ways. I can do it in, I did it. I figured out the distance that it will go. But how do I know that it's correct? Well, first thing I should do is I should check the units. By the way, before I get into units, I'm just going to ask you real quick. I'm going to do a recap. I want you to write this down. I want you to take a picture of this computer screenshot. Take a picture of it now. Hold down the control button, press the little picture thing right above the 6 key, and then boom, you got a picture of this, and I can erase this. I don't want to erase it, but I don't have enough room. I'm sorry. All right? Yes, I want you to take a picture. I want you to write down the equation for R, but I really want you to write down the idea of it. And I'll recap for those of you who might have gotten lost as to how I got here, how I came up with this stuff. All right. What I did was I said, okay, I want to figure out how far this thing goes as a function, or how far this thing goes based off of how fast I threw it and the angle that I threw it at. What I did was I broke the velocity into its components, Vy, Vx. Then I looked solely at the y direction, and I asked myself, how long is it airborne for? How long is it in the air for? And so I calculated out time based on the idea that I threw something else up purely vertically and had it come down. Because if I threw up that football or whatever, if I threw a football at an angle, and I threw a basketball at the exact velocity, same velocity that the vertical component of the football that I threw was, it would be in the air for the same amount of time. So I calculated that out. There's the time. Then I said, okay, now in that amount of time, how far did it go? That's why I looked at the x direction. That's how I was able to get my answer. Let's look at this problem, because I want to show you some things, and then I think I've got to be done, because I told you I would be finished at 12, and it's 3 minutes till 12. So let me erase this and go. We good? Can I erase? Say yes. Someone tell me yes, because if you say yes, I'm going to erase the whole thing. All right, good. Erase. Let me write down what I had. I had R is equal to V naught squared times sine of 2 theta divided by G. Let's check the units on this to see if we got this correct. The units of this is this. The V naught, all right, so my range is measured in meters, right? So I should get meters is equal to, what is your velocity initial measured in? I didn't give you the numbers for it, but what would it be measured in? It would be measured in meters per second, exactly. Meters per second, but I'm squaring it, right? Sorry. Meters per second, but I'm squaring it, so it's technically meters squared over seconds squared. The sine of 2 theta, there is no units on trig identities, or trig angles. No units. I know that you would think that, hey, 2 theta is measured in degrees, but that's not true, actually. Actually, it is true, but I mean, we just don't include those units. What is gravity measured in? Meters per second squared, exactly. I've got a fraction over a fraction. I'm going to take this fraction on the bottom. I'm going to flip him upside down. So I'm going to say meters squared per second squared or times seconds squared over meters. This guy cancels out with that guy. 2 meters on top, 1 meter on the bottom, one of those cancel out. So I have meters is equal to meters. Is the units correct? Good. Now think about this. Mathematically speaking, if I increase gravity, if I make gravity bigger, what would happen to the range? Look at this equation right here. If I make gravity bigger, in the limit that gravity goes to infinity, what would happen to range? Or in the limit that gravity gets bigger and bigger and bigger, what would happen to this number? Think hard. It gets smaller. Doesn't that make sense with your physical mind? If I throw something in a place that has gravity as higher, it wouldn't go as far, even if I throw it at the same velocity. If I throw something on Jupiter, I throw a football on Jupiter, and I throw a football on Earth, it wouldn't go as far. That makes perfect sense with me. That's what the math is telling me. So the math is aligning up with my brain. All right, what about the velocity? If the velocity gets bigger, what happens to the range? Does it get bigger or smaller? I'm out of time. I need you guys to hurry up and answer these things. It gets bigger, exactly, because it's in the numerator. If that number gets bigger, the numerator gets bigger, and the range gets bigger. Wouldn't that make sense? If I throw something with a faster velocity, it would go further. Now here's the thing that trips you out. Here's where physics starts teaching us things. Because those things we already know. If I threw something faster, it will go further. What if I threw something twice as fast? If I threw something, like let's say I threw something at 10 meters per second, and it went 20 feet. If I throw something at 20 meters per second, I throw something twice as fast as I threw it in the first place. How far will it go? So if I threw something at 10 meters per second, the range was 20 feet. Or, I'm sorry, 20 meters. Let's say 20 meters. Let's pretend I throw something at 20 feet per second, 20 meters per second. What would my range be? I'm just curious. Would it be twice as much? Would it be 40? That's my question. Say yes or no. And if you're stuck, just say, I don't know, and then I'll tell you the answer, and you can keep thinking about it. You think it would be twice as long? If I double my velocity, will it double this? No. Because if you look at the equation, your range is dependent on the square of the velocity. So if you double the velocity, that will actually make your range increase by 4 times. Because if I replace this V0 with a 2 V0, I got to square that 2. And that makes it 4 times the amount. I think that's pretty crazy. Did you know that? Did you know that? Did you already know that in your head? If I double the velocity, it will shoot something out 4 times further. Is that some information that you already had stuck in your head? No. Then that means the physics has taught you something. That means you have learned something from the mathematics. I didn't teach it to you. All I'm doing is it's solving this equation for you. But we're taking a look at the mathematics and having it change our brains. That is the beauty of physics. That is what excites me about physics. I'm trying to excite you about physics as well. I'm going to do one more thing, and I know that I'm over time. I apologize, but I just want to show it to you real quick. Think about this. The sine of 2 theta. You know that the graph of sine looks like this, right? Wait, it looks like this, right? What is the biggest value that it goes up to? What is the highest it goes up to? Well, fine, I'll just tell you this. No, the highest it goes up to is 1. The graph of sine, right? It goes up to 1, down to -1. Back and forth, back and forth, back and forth, right? And where does this highest value occur? That highest value occurs at pi over 2, also known as 90 degrees. I'm pretty sure, right? Pi over 2, 90 degrees. So, the biggest value that this thing will occur if I'm changing the theta is going to be when this thing, 2 theta, is equal to 90 degrees. Okay? I'm going to divide both sides by 2, and I've got theta equals 45 degrees. This is telling me that if I want the range to go the furthest it possibly can, I need to throw this thing at an angle of 45 degrees. Now, logically, in your head, you know that makes sense. Mathematically, I've just proven it to you. I think that that's rad. That excites me. How does that not excite you? All right. It's been an honor and a pleasure coming over doing this lecture with you. This is always one of my favorites because it blows your mind. Don't memorize this. This is called the range equation. It's not an equation. Memorize this. This is something I've proven to you. This is the kinematics equation. This is the basic one. This only applies to a scenario where you have something that is starting on the ground, ending at the same exact height, and shooting up at an angle. This always applies. Memorize this. Derive this. Figure out how to get here. But don't memorize this answer. Because I guarantee you on a test, I'm going to change up the scenario on you, and all of a sudden this thing won't work. But this will always work. So figure out, if you need to go back in your notes, figure out how I use this. And that's all. I only used one equation today. Just this one. And I also used SOHCAHTOA. I use these 2 concepts right here to derive this. And this has taught me about life. That's exciting. All right, I'll talk to you guys later. Okay, bye.